Ok, stiamo registrando. All right. Okay, so in the previous lesson, we started the chapter of hadrons, and in particular, we started discussing one of the most important quantum numbers for light hadrons, that is the isospin. So we have seen that isospin is an almost exact symmetry. It is not completely exact because there is essentially a small violation due to the Coulomb interaction. And the level of accuracy of this symmetry is given by essentially the difference in mass between the proton and the neutron divided by the mass of the proton. So it is an effect of the order of 1 per mil. Okay, so it is an almost exact symmetry. We have seen how to define doublets. So the proton and the neutrons are indeed doublets, an isospin doublet, and they are distinguished by the third component of isospin, either plus 1/2 or minus 1/2. And we have seen that we can use exactly the same notation for the up and the down quark at the more fundamental level. And finally, we discussed how pions have been discovered and how their main properties have been measured. And finally, we realized that indeed pions constitute a triplet of isospin, with their component being +1, 0, and -1, respectively, for the pi plus, pi 0, and pi minus. Now, the concept of isospin is not only useful for classifying the hadrons, but also for constraining their dynamics, as we will see today. In fact, any reaction or decay that occurs through the strong interaction must have the same total isospin either in the initial and in the final state, because isospin must be conserved in all strong processes. And so to understand this quantitatively, so how isospin conservation constrains the relative values of the cross-section in strong processes, we have to introduce the Klebsque coefficients, which allow to properly write the isospin wave function of compound system. So I assume that you already know the Klebsque coefficients. You have already studied in quantum mechanics, but nevertheless, let me define them from scratch. So I will now share my Blackboard. Ok, vedete la lavagna a schermo pieno?
Sì.
Ok, perfetto. Okay, so let me start introducing the Klebsque coefficients, and then we will see how to use them in order to write down the isospin wave function component of compound systems. So suppose we have a system of two particles with isospin states I1, and then the third component, I13, and I2, and I23. Okay, where I23 is the second component. Now we can construct two bases from these two states. The first basis is the one of this kind of vectors. So I1, I13, I2, I23. And these are simultaneous eigenstates of, let's say, simultaneous eigenstates of the operators I1 squared, I2 squared, I13, and I23. Just to give you some example, we can write down the eigenvalue equation, for instance, for the I1 square operator. So we have I1, I13, I2, I23. The eigenvalue, as you know, is I1 plus 1 h bar squared, and then we have our eigenstate I1, I13, I2, I23. And similarly, as an example, let me write down the eigenstate, the eigenvalue equation for the third component of isospin, for the first particle, for instance. So I13, acting on the same state here, and the eigenvalue will be I13 h bar, and then we have the same state here. Now, there is, however, a second basis that we can construct, which is of the form I1, I2, I, and I3, where I is the total isospin of the system, and I3 is the third component. So I equal total the isospin of the system, and I3 is just the sum of the third component of the two particles. And these eigenstates here are now simultaneous eigenstates of the operators, again, 1 square, I2 square, I squared, and I3. Again, let me give you some example. So again, we start with a I1 squared. This is now our eigenstate, I1, I2, I3. And then we have I1 plus 1 h bar squared, and then we have our eigenstate. I1, I2, I3. Okay, let me just give you another example for the I square. So the state is the same, so it is now I plus 1 h bar square, and then the state is the same. Or just as a last example, the I3. So we have the same state, and then we have I3 h bar, and then we have the same state. Now, of course, one can relate the two bases, and this can be done through the completeness relation. So let me show how this works. So we start from our first basis, I1, I1, 3, I2, I2, 3. Now, this is equal to, we apply here the completeness relation, so the sum over I and I3 of I1, I2, I3, I1, I2, I3, and then we write down our initial state, I1, I1, 3, I2, I2, 3. Well, all these objects here, as you know, is the completeness relation, so this is exactly the identity operator, okay? But now this allows us to write down the Klebsque coefficient in the proper way. So let me take a new page. C'è qualcuno che deve ancora copiare? Ok, direi di no. So this we can rearrange in the following way. So I1, I1, 3, I2, I2, 3, written as the sum over I and I3 of I1, I2, I3, I1, I1, 3, I2, I2, 3, and then we have our state I1, I2, I3. Well, all these guys here are what we call the Klebsque coefficients, okay? So that we can write them in a compact way as CI3, okay? So the CI3, which are the Klebsque coefficients, are given by this quantity, I1, sorry, I2, I3, I1, I1, 3, I2, I2, 3. And so we can write down our previous relation as I1, I1, 3, I2, I2, 3 as the sum over I and I3 of our Klebsque coefficients. And then we have the state I1, I2, I, and I3. Okay? Or we can simply write these even in a more compact way as I, I3, C, I3, and then we just write here the total isospin and third component. This is an equivalent way, just a shorter notation. Okay, so I think all these you know already. So let's now take an example. Okay, so let's suppose we have a system of two particles. So suppose we have a system of two particles again with in the state, one is in the state I1 and I13, and the other is in the state I2, I23. So as we've seen, the total third component is simply given by the sum of the two third components. So I13 plus I23. What about the total isospin I? Well, as you know from quantum mechanics, which is, and as you know also by comparing with the spin notation, which is exactly the same, the total isospin of a system can be any value in the interval I1 minus I2, absolute value, I, and then we have I1 plus I2. So this is exactly the way you get the spin multiplicity in quantum mechanics. So the isospin formalism is exactly the same. So here we can have more than one possibility, indeed, okay, depending on the value of I1 and I2. So let's take some concrete example. So we suppose that, for instance, we consider a system of a pi minus plus a proton. Okay. So in this case, our isospin state I1, I13 will be for the pi minus, as you know, this will be +1, and the third component is -1. So let me take this for the pion. And then for the proton, I13. For the proton, this will be, as you know, 1/2, and then +1/2 for the third component. So we can immediately calculate the third component of the total isospin. So I3 will be I3 of the pi minus plus the third component of the proton. That is -1 plus 1/2. This is equal to -1/2. And let's now calculate the total isospin. Okay, so we have here I of the pi minus minus I of the proton, total isospin, and then we have the sum. So I of the pi minus plus I of the proton. So let's now substitute the numerical values. So we have 1 for the pi minus and 1/2 for the proton. And again, we have 1 plus 1/2 in this case. So overall, we obtained something like 1/2 I smaller than 3/2, smaller or equal, okay? So overall, we have indeed the two possibilities. The total isospin can be either 1/2 or 3/2. Both values are in principle possible, okay? Now we have to write down these, since we have two possible values, we have to write down the isospin wave function, so the isospin state, okay, in terms of the Klebsque Gordon coefficient that we just introduced. So let me take a new page. So in general, we have I1, I13, I2, I23 is equal to the sum over I3, C, I3, I3. So this is the general relation. Let's now apply this to our specific case. So in our case, we have I of the pi minus, I3 of the pi minus, I of the proton, I3 of the proton. this must be given by the sum of two contribution, because we have two possible values of the total isospin. So we should have here a first Klebsche coordinate coefficient, 1/2 minus 1/2, for the state 1/2 minus 1/2, plus a second contribution with the Klebsche coordinate coefficient for 3/2 minus 1/2, 3/2 minus 1/2. And so now the full point is now to properly evaluate these two Klebsche coordinate coefficients in order to have the full expression of our eigenfunction. And as you probably know, the Klebsche coordinate coefficients squared are tabulated and grouped in subtables that we will see in a moment. But let me just draw here the structure of these subtables. So they look like this. So here we have the total isospin of the two components of our system. Here we have all the possible values of the total isospin, and here we have the third component. Okay. Now, in the first column here we have the two values of the third component, so A13 and A23, and possibly other values here. Okay, and what we have here in this last sector is what you need. So these are plus or minus squared Klebsche coordinate coefficients. So let me just give you the numerical value of our present example, and then I will show you the general situation. So in our example, where we have now a pi minus with a proton, the situation is going to be like this. So we have, for the pi minus, we have 1, and for the proton, we have 1/2. Then we have seen that we have two possible values of the total isospin, which are 3/2 and 1/2. And then the third component is minus 1/2, the total third component. Then we have the partial third component. So we have I3 pi minus is equal to minus 1. And I3 proton is equal to plus 1/2, okay? And so now by looking at this specific subtable on the tabulated values, we should get the value of the squared Klebsche coordinate, which turn out to be 1/3 and minus 2/3. So once we get this, we can write down our total wave function. So I pi minus 3, IP3 will look like square root of 1/3, 3/2 minus 1/2, minus square root of 2/3, 1/2 minus 1/2. Where now these the Klebsche coordinate coefficient have to be taken as the square root of the values that you take from the table with the proper sign. Now, to show you all these on the table, let me switch now to the slides. Okay, so here you should now see the tables for the Klebsche coordinate coefficient. And our case is highlighted in yellow here, okay? So we have 1 times 1/2. Then we have the two possible total isospin values, 3/2 and 1/2, with the third component, which is minus 1/2. These are the two third component of the two particles, minus 1 for the pi minus, plus 1 for the proton, and these are the square of the two Klebsche coordinate coefficients. Okay, and for different system, of course, you have to pick up your table from this slide here. Okay, that you find in any textbook. Any questions?
No, grazie.
Ok, immagino sono cose che avete già visto a meccanica quantistica. Okay, so let's now apply all this formalism to set some constraint on strong so cross-section of strong reactions. Okay, so let's go back now to the blackboard. Okay. So let's now consider two strong reactions, and we want to see how their cross-section ratio is by just applying conservation of isospin. So the first reaction, the first strong reaction I want to study is proton plus proton that goes into deuteron plus pi plus. Okay. Now let me remind you that for the proton we have I3 of the proton is 1/2 plus 1/2. The I3 for the deuteron is 0, 0. It is an isoscalar particle. And I3 for the pi plus is, as you know, 1 plus 1. Okay, so let's now make use of all this information to construct our, first of all, our initial state wave function. Okay. So the total third component of isospin, I3i, is given by the sum of the two P3 plus IP3. We have two protons in the initial state. So this is plus 1/2 plus 1/2. This is plus 1. Okay. This is for the initial state. What about the final state? So in the final state, we're going to have ID3 plus I pi plus 3. So for the deuteron, the third component is 0. For the pi plus, it is 1. So it is plus 1. Okay. So indeed, the third component is conserved in the reaction. We have the same value in the initial and in the final state, as we would expect because it is a strong reaction. Okay. Now, let's try to write down the wave function for the initial and for the final state. So, for the initial state, we have now to calculate the total isospin, that is IP minus IP plus IP. Okay. So this is 1/2 minus 1/2. 1/2 plus 1/2. And so the possible values of the initial, so this is the initial I. The possible values for the initial isospin are 0 and 1. Okay. Now a question for you. So by applying the formalism for the multiplicity, we found that there are two possible values for the initial total isospin, either 0 or 1. But the question I want to raise to you is, are those two values both possible or not? And why?
Just one, because the final state has I equal to 1.
Yes and no. Try to say better. So which one is not possible and why?
Zero is not possible because the final state has the isospin is equal to 1.
Okay, yes. Indeed, you can also consider the third component. So if your third component is plus 1, okay, then obviously your total isospin cannot be 0. Okay, so the only possible value here is 1. So this we forget about 0. Okay, so that was the correct answer. And so we can write down now our initial state wave function as 1, 1. Okay. The first one is the total isospin. The second one is the total third component of the isospin. Let's now work out the final state. So in the final state, we have ID minus I pi minus IF ID plus I. So this is pi plus. Sorry, pi plus. So we're going to have 0, minus 1, 0 plus 1. So here we have only one possible value, that is 1. Okay? And so our final state wave function will be IF, I3F, also equal to 1, 1. And so this corresponds to the initial state, the initial isospin wave function. Now, suppose that our Hamiltonian has some isospin-dependent interaction term that we can call I. So suppose that our total Hamiltonian is, let's say, an unperturbated term plus an interaction term which depend on isospin, on the total isospin. Okay. Then, as a result, we can write down the matrix element, and so in turn the cross-section for our process. So the cross-section for this PP into D pi plus strong reaction must be proportional to the square of the matrix element phi f. Then we have this isospin-dependent Hamiltonian, and then we have psi I all squared. Okay. So we can now substitute here our initial and final state that we found. So 1, 1, hi 1, 1 squared. And this we can write in a compact notation as m1 squared. Okay, so this is essentially our squared transition amplitude, where the 1 here indicates that our isospin is 1 in this case. Okay. Now, this was for the first reaction. Let's now work out the second reaction, and then let's try to see how the ratio of the cross-section will look like. So I take a new page. Okay. The second reaction that we want to study is proton plus neutron that goes into deuteron plus pi 0. Okay, so let me just quickly repeat this exercise. First of all, let me remind you that I3 for the neutron is 1/2 minus 1/2, and that I3 for the pi 0 is 1 and 0. So, third component for the initial state is given by the sum of the two, I3p plus I3n, that is plus 1/2, sorry, minus 1/2, this is equal to 0. What about the final state? Third component, I3f, this is I3 for the deuteron plus I3 for the pi 0, that is 0 plus 0 equals 0. So we are fine because they are equal, so the third component of isospin is conserved but sure in this reaction, as we expect. Let's now calculate the total isospin. So we have for the initial state, I proton minus I neutron. So this is going to be 0 minus equal to I minus equal to 1. And so here we have two possibilities. Again, either 0 or 1. But in this case, they are both possible because the third component is 0. So the total isospin can be indeed either 0 or 1. Okay. So we need to calculate the Klebsque order coefficient because we have to combine two isospin states. So in general, for our initial state wave function, we're going to have something like C0, 0, 0, 0 plus C10, 1, 0. So we have to combine the two possibilities. Okay, so we have to look now up to the Klebsque-Gordon tables. Let me just reproduce here the one that we need. So this is 1/2 times 1/2. Then we have I equal 1 and I equal 0. And then we have I3 equals 0 and I3 equals 0. And then we have I3p equal 1/2 and I3n equal to minus 1/2. Okay, so let's move back to the slide. So let me take the values from the tables. Okay, so the situation is the one highlighted in blue. So this is our system, 1/2 times 1/2, 1, 0, 0, 0, plus 1/2 minus 1/2. So the square of the Klebsque order coefficient that we need are both plus 1/2. So let's substitute into our wave function. So what we have here is 1/2 and 1/2. And so our initial state wave function will be square root of 1/2, 0, 0, plus square root of 1/2, 1, 0. Okay, what about the final state? So let's work out the final state in the usual way. So ID minus I pi 0, IF, ID plus I pi 0. So this is going to be 0, minus 1, and 0 plus 1. So in this case, we have only one possible value, that is 1. And so the final state Isospin wave function must be IF, I3F, must be 1 and 0 for the third component. So we are now in the situation in which the initial state is a 50% mixture of I0 and I1, okay? Whereas the final state is a pure I1 state. And isospin conservation then requires that the reaction can only proceed through the common I1 channel. So let's see this now more in detail. I need to take another page. Okay, so let's work out now the cross-section for this second process, proton plus neutron that goes into deuteron plus pi 0. This must be proportional to the squared amplitude of psi f, this generic isospin-dependent Hamiltonian term, and psi I squared. And let's substitute here now what we found. So for the psi f, we have only one possibility, that is 1, 0. Then we have our Hamiltonian. And for the initial state, we have two possibilities. So this is square root of 1/2, 0, 0, plus square root of 1/2, 1, 0. All this squared. So let's work out this. So we have as a first term square root of 1/2, 1, 0, hi 0, 0, plus square root of 1/2, 1, 0, hi 1, 0, all squared. So here we have indeed the sum of two amplitudes. Okay. However, only one of the two is isospin conserving. That is the second one. Okay. The first one is isospin violating because initial and final state have different isospin. So this is not allowed for strong reactions. And so the only term that survives is the second one by enforcing indeed isospin conservation in the process. So this is now going to be simply we can write as 1/2. And then we have 1, 0, hi 1, 0 squared that we can write down in the compact way as 1/2 m1 squared. Okay, where again m1 is the amplitude corresponding to isospin equal 1. And now we can put both results together. So suppose we want to predict the ratio of the two cross-sections, so the cross-section of protons plus neutrons that goes into neutron plus pi 0, divided by the cross-section of protons plus proton that goes into neutron plus pi plus. Okay, so the cross-section will be the cross-section ratio will be proportional to 1/2 m1 squared divided by what we found before, m1 squared. So indeed, the ratio is exactly 1/2, as we would predict just by assuming isospin conservation in the process, and it is indeed exactly what one observed experimentally. Indeed, the experimental measurement of these two cross-sections are indeed in the ratio of 1/2. Any question? So in other words, isospin is a powerful means to make prediction of cross-section. Suppose you have measured one of the two, you can predict the other by simply assuming isospin conservation in the process. Okay. Now, let's move on to the slide again. So let me summarize here what we have just found. So the strong reactions, proton-proton into deuteron pi plus and proton-neutron into deuteron pi 0, can proceed only through the common I = 1 channel. And consequently, one expects that the ratio of the cross-section is exactly to 1/2, as it is indeed experimentally observed. Now, another interesting example is the pion-nucleon scattering. Okay. Now, since the total isospin of the pion is 1 and the total isospin of the neutron is 1/2, one can have either total 1/2, total isospin 1/2, or 3/2. Let's consider now these four reactions. The first three, as you can see, are just elastic scattering because we have the same particle in the initial and the final state. The last one is a so-called charge exchange reaction, okay, where you just exchange the charge, the electric charge. Now, for the first two, one finds that the third component of isospin is either plus 3/2 for the first one and minus 3/2 for the second one. Okay, and so the total, as we've seen before, the total value 1/2 is forbidden. Okay, and so these two reactions are described by a pure total isospin equal to 3/2 amplitude, m3/2, and have exactly the same cross section. Okay, from the reason. So the two cross-sections are proportional to the same matrix element. What about the other two? For the other two reactions, one found that the third component of isospin is minus 1/2, and therefore the total isospin can now have both values, 1/2 and 3/2. And so once you put the full calculation with the Klebsque coefficients, at the end you obtain these two expressions for the cross-section for the third and for the fourth reaction. Okay, where the numbers that you see here, these coefficients, are of course the result of the product of suitable Klebsque coefficients, more like the way we've done before in the previous example. So we can now write down the ratio of these four reactions, again based on isospin conservation. So the first two must be equal, and the second two should stay in this ratio in terms of the value that one obtains from the Klebsque coefficient. So we have 1/9 here, 2/9 here, and then we have two possibilities for the last two reactions. Okay. Now, keep this in mind. We will come back to this in a couple of slides. Let me spend a few words about hadronic resonances, something that we already introduced before and that we will study even further later on in the course. But now I need just to come back to this concept. So as we discussed several times, the lifetime of hadrons that can decay strongly is extremely short. Okay, order 10 to minus 33, 10 to minus 24 seconds. And so from the experimental point of view, it is impossible to reveal their tracks because they are exceedingly too short. So essentially, they are seen to decay exactly where they are created. And so there is no way experimentally to detect, to track them, essentially. Okay, so the production and decay vertex cannot be separated experimentally because they are too close. However, one can detect these objects in the form of resonances. Okay, we will see more about this later on. So tens of these hadronic resonances were discovered in the 50s and early 60s, as soon as the high energy accelerators came into operation after the Second World War. Okay, and also their quantum nums have been measured for a few of them. Okay, also by making use of bubble chambers, which were the high energy particle detector available at that time. And the largest and the lowest energy resonance is the delta plus plus 1232, where this number here is the value of the mass of this hadron in MeV. This was also the first to be discovered. It was discovered by Fermi and collaborators in 1952. And it's also essentially the most studied one. It is a huge resonance. You can create it already at low energy, and you can study it very carefully and very precisely. It was indeed clearly observed in Pion nucleon scattering at a center of mass energy of the order of the mass of this object, of course, and with a decay width of 120 MeV. Now we know how to convert these into a decay time, okay, the way we've used already several times. So we have the h bar c constant in the numerator, which is essentially 200 MeV times Fermi. Then we have our decay width, we multiply by the speed of light, and we end up with a decay time which is typical of, indeed, hadronic decays. Okay, so 10 to the minus 24 seconds. So let's look now at the cross-section. Okay, so this is the measurement of the cross-section, either the elastic cross-section for the pi plus proton process, the first that we discussed before, okay, and also the total cross-section, okay, when also includes non-elastic contributions as a function of energy. So you have here essentially the energy in the center of mass for this reaction. So what do we see here? We have a huge bump in the cross-section. Consider that the vertical scale is logarithmic, so this is really huge, okay? Then we have several other minor resonances up to essentially center of mass of 3 GeV. Beyond that, essentially the cross-section becomes flat, so there is any more contribution from resonances. And this is what is written here. So essentially, when you go beyond square root of 3 GeV, no further resonances can be recognized, and the elastic cross-section becomes a minor part of the total cross-section. So as you see, at low energy, the total cross-section coincides with the elastic scattering cross-section. But as soon as you move to higher energy, the elastic cross-section decouples from the total cross-section, okay, becomes smaller and smaller and smaller, because at high energy you have many more contribution from inelastic processes, okay? Now, so this is indeed our delta plus plus 1232 resonance, okay? And it is a pure 3-half state, 3-half isospin state. And it can be indeed accessed as an intermediate state in any of these 4 Pion nucleon scattering reactions, okay? In the sense that you have, for instance, suppose you are colliding a pion beam over a proton target, okay? The reaction proceeds through the intermediate formation of, for instance, this resonance, which then further decay into a pi plus and proton, or pi minus and neutron, etc., etc. Okay? So in this sense, the resonance is formed as an intermediate state of our scattering reactions here. Now, it is, as I was mentioning, a pure 3-half isospin state, and therefore at the resonance, so when the center of mass energy of this reaction is more or less the same as the mass of this resonance here, then only the M3-half amplitude can contribute to the cross-section. The M1-half that we saw before do not contribute at the resonance, okay? Because this is a pure 3-half state. And so again, one can make use of these to calculate ratios of cross-sections. Okay, for instance, we have the first, so A divided by the sum of the third and fourth. You get rid of this M1/2 amplitude, so you only consider the 3/2, which is the only one surviving at the resonance, and then it turns out that this cross-section ratio is exactly 3, as it is indeed again measured experimentally and confirmed experimentally. Okay. Now, any questions so far? Okay. If not, let's continue. So in 1943, by studying cosmic rays with a cloud chamber immersed in a magnetic field, a new family of particles was discovered, all with a mass around 500 MeV. So this is a layout of the experiment, the famous Rochester Bootr experiment. So essentially, they had a cloud chamber immersed in a magnetic field, triggered by several Geiger-Müller counters above and below the chamber, and also using some LED shield in order to only consider high energy particles. Okay, so let me just go through the detail of the experiment. So a cloud chamber within a magnetic field of 3,500 Gauss, triggered by Geiger-Müller counters positioned above and below the chamber, was used. The lead shielding ensured the selection of only energetic cosmic ray events, such as the one you see here, that pass the lead, give a signal on the first Geiger-Müller, give a signal on the cloud chamber, possibly triggering a reaction here on the lead plate. And then you find also the tracks, the original one, and also the ones creating the reaction measured in the bottom Geiger-Müller counters. Okay, the experiment was performed at the sea level, and the signal was constituted only by a few events out of something like 5,000 photographs taken during 1,500 hours of operation. So what they observed? They observed some strange patterns of charged tracks, the ones that are highlighted in this slide here, okay, that look like forks, as you see, in the gas. So the interpretation was that some new particle decays into an unknown, there should be some unknown neutral particle, which is not observed here in the top, of the mass in the range 385 up to 800 meters. There was a lot of large uncertainty at the time, which at a certain point decays into a pair of charged particles. So those that you see here, 1, 2, okay? There was also another topology of events, okay, where you do see some charged particle here, which then decay in another charged particle and something neutral, which is not detected, okay, some missing track here. Interpretation was a disintegration of an unknown charged particle, in this case, still of the mass of 500 MeV, more or less, into a penetrating charged particle and an unobserved neutral particle. So this is the penetrating charged particle, and this is the unobserved neutral particle. So all this came as a surprise, just by looking at cosmic rays. This was not expected. And the experiment revealed the existence of the following new particles. So some were neutral and decayed into 2 charged particles, plus possibly also some neutral particles which were not detected. And these were called V0. Other, which were called theta, were charged and decay into a charged particle, plus possibly also neutral particles. And other decayed into 3 charged particles and were named tau. Okay, so essentially they claim to the observation of 3 new objects, 3 new particles, with some strange behavior. Now, it took a decade to establish that the theta and the tau actually were exactly the same particle, and that the V0 was only just the neutral counterpart. Okay, so today we know everything about these objects. We call them kaons or K-mesons, and there are 4 of them, okay, in the ground state. 2 are charged, electrically charged, so K plus and K minus, and 2 are neutral, the K0 and the K0 bar, okay? And they form 2 isospin doublets. So you see here the mass that we know today. It is indeed of the order of 500 MeV, the electric charge, the isospin, which is 1/2, and so as you see, we have now 2 possible projections for the third component. And so indeed, these constitute 2 isospin doublets, okay? Now, these 2 neutral kaons, the K0 and the K0 star, we will study quite in detail later on in the course, because as we see, they form a very interesting oscillating quantum system, okay? And it is indeed the system where, for the first time, CP violation has been observed in weak interaction, as we will study. Now, So soon after their discovery, it was observed that the kaons were always produced along with another unknown particle, decaying into a proton and a pion. So you see here a typical topology for this event. Okay, so you produce a kaon, for instance, a K0, which decay into this fork, which is indeed a pi plus pi minus pair, together with something else, which was not known at the time, so a neutral particle. As you see here, there is no track here visible in the bubble chamber. Then decaying into two charged particles, which were recognized to be a proton and a pi minus. Okay.
Professor?
Yes.
Excuse me. Here and in the slide 8 as well, how is the magnetic field directed?
It is, I think, it's orthogonal to the
Okay,
direction,
to the page.
Yes, such that you have this curvature.
Okay, perfect. Thank you.
Now, so these new particles, for instance, this one here, okay, are in fact of a different type than the mesons that were discovered before, and are commonly named as Hyperons. Okay, the lightest of the Hyperons is this delta zero hadron, okay, which is neutral. Then we have three heavier objects, which are the sigma plus, sigma zero, and sigma minus. And then we have even heavier objects, which are the psi zero and psi minus. All of these discovered in the cosmic rays. Okay, so in this kind of decay patterns. So this was before the advent of high energy accelerators in the physics laboratories. Now, this table summarizes more or less the properties of these newly discovered hyperons, okay, with the lambda, the 3 sigma, and the 2 psi. These are the electric charges, these are the masses, okay, which are now, as you see, much heavier than the previous ones, okay, essentially more than double the mass. And then you have the decay time and the principal branching ratio, so the main decays. And let me focus on the decay time, which are in picoseconds. So you see that with the only exception of the sigma zero, all the other have decay time of the order of hundreds of picoseconds. So extremely slow decay, which are only possible if they are driven by the weak interaction. Okay. The only exception is the sigma zero, which, as you see, with a photon here, this decays electromagnetically. Okay. Otherwise, they all decay weakly, so through the weak interaction. And this is quite important for the discussion we're going to have now. So these new particles showed some unexpected, or if you like, strange features. First of all, they were always produced in pairs, and this was not understood at the time. Secondly, they were produced by fast, strong interaction processes, while they decayed only slowly with a lifetime typical of the weak interactions, as we've seen in the previous table. Okay. And for this reason, so these two unexpected observations, they were called strange particles. Okay, so these behavior were not understood in the first moment. Now, the solution was given in 1953 by Nishijima and Gelman, with the introduction of a new quantum number that today we call strangeness, and we indicate with the symbol capital S, okay, which is additive like the electric charge. So once we introduce these, everything now becomes clear. So strangeness is conserved by strong and electromagnetic interaction, but it is not conserved by weak interaction. Okay, and this is indeed the reason why this object can only decay weakly, as we will see in a moment. The production by strong interaction from an initial strangeness equals 0 state can only occur if two particles of opposite strangeness are produced, because strangeness is conserved in strong reaction. So if you have S0 in the initial state, you must have S0 in the final state. And this is the reason why they are produced in pairs. Okay, so this already explained the first problem here. Then the lightest strange particles, so the kaons and hyperons, being the lightest, they can only decay into non-strange final state, as we've seen pions, for instance, or protons, okay, for energy conservation. And therefore, they cannot decay strongly because the final state have no strangeness. And so if they would decay strongly to strange object, they would to no strange object, they would violate strangeness. Strangeness conservation is strong interaction. Okay, and so this explains also now the second problem here. Of course, if the mass of a strange particle is large enough, then the final state of the same strangeness might be energetically accessible, and in this case, the reaction, the decay can also occur through the strong interaction with a lifetime typical of strong interaction, so 10 to the minus 24 seconds. Okay. An exception to this is the sigma zero meson, the sigma zero barrier that I showed before. Okay, so the sigma zero is the only one that decays into into a lambda, and so here the strangeness is conserved. Okay. So what about lighter hadrons? So the non-strange light hadrons contain only U and D quarks, whereas the strange hadron contain one or more strange quark. So this is the new income here in the physics of hadrons. So by convention, the quark strangeness is the quark strange is assigned a strangeness of -1, and the anti-quark strange, so the anti-strange quark, is assigned a strangeness of +1. So the choice of the sign here is just a convention, -1 +1. As a consequence, S equal -1 hadrons, such as the K-, the K0, the lambda, contain one S quark, and S equal +1 hadrons, such as the K+, the K0, the anti-lambda, contain one S bar quark, so an anti-strange quark. What about the Xi? The Xi baryons have strangeness equal -2, and so they contain 2 S quarks, etc. So in general, the strangeness is given by minus the number of strange quarks that you have in your hadron minus the number of the strange antiquarks that you have. And so we can classify hadrons also now according to the strangeness. So all the ones that we studied before, the pions, protons, neutrons, excited state of the nucleon, delta, etc., these are all non-strange objects because they do not contain strange quark as valence quarks. Then we have strangeness +1 object, like the K+, K0, lambda 0 bar, etc. Okay. Then we have the strangeness equal -1. And then we have also strangeness equal -2 or -3. So -2 because they contain 2 strange quarks, and -3, which is the omega minus meson, which contain 3 strange quarks as a valence quark, as valence quarks. Okay. Okay, I think we can stop here, and then we recombine, let's say, 15, okay? 10, 15, and then we will solve some exercises.
Okay.
Okay. See you in 10 minutes. Okay, so let's start again. Allora, mi confermate che vedete la slide?
Sì, la vediamo.
Okay. Okay, so we will now gonna solve 3 problems about isospin and as we've seen today. So the first one, in which isospin states can the following 3 Pion system exist? So pi plus, pi minus, pi 0, or a 3 pi 0 system. So I will now switch to the blackboard. All right. So this is problem 5.1. Okay, so let's start from the first system, that is a pi plus, pi minus, pi 0 system. So we want to see in which isospin states this system can exist. Okay, so when we have 3 particles, the technique is to first combine the first 2, the way we have already studied today, so with the Klebsque coefficient, etc. And then we add the third particle, okay? So this is the way to proceed. So let's first combine the pi plus and the pi minus. So combine first the pi plus and the pi minus. So the third component for this 2 Pion system is the third component of the pi plus the third component of the pi minus. That is plus 1 minus 1 equals 0. Now the total isospin, I pi plus minus I pi minus, and I pi plus plus I pi minus. So this corresponds to 1 minus 1 and 1 plus 1. So the possible assignments for the total isospin for the 2 Pion system is 0, 1, or 2. So we have now to pick up the Klebsque table. I will just draw it here. So we are in a situation with 1 times 1, then we have 2, 1, 0, 0, 0, 0, plus 1 and minus 1. So if you go now to the table, you will find 1/6, 1/2, and 1/3. So the wave function for this 2 Pion system, pi plus, pi minus, the isospin wave function will be a combination of these 3 states. Square root of 1/6 for the 2, 0, plus square root of 1/2 for the 1, 0, plus square root of 1/3 for the 0, 0. Okay? Now we add the third Pion. So now we add the pi 0. Okay? So now we have to compute the third component for the 3 Pion state. That is I3 for the 2 Pions plus the 1 of the pi 0. That is 0 plus 0, 0. And we have to compute now the total isospin. So we have I pi pi minus I pi 0. This is now the total for the 3 Pion system. And then we have the sum I pi pi plus I pi 0. And so here we have 3 possibilities. So the total isospin will be just 1 for the case I pi pi equals 0, or it can be 0, 1, and 2 for I pi pi equal 1, or it can be 1, 2, and 3 for I pi pi equal to 2. You can just check yourself by substituting. Okay. So let me take a new. Let me take a new page here. So we have to consider the three cases separately, okay? So for I pi pi equals 0, the only assignment is that I3, for the 3 Pion system, this can only be 1, 0. Now, for the case of I pi pi equal 1, we have 3 possibilities for the 3 Pion system. So we have again to take the proper Klebsque order coefficient. The table that we need is this one. 1 times 1, 0, 0, 2, 1, 0, 0, 0, 0, and you will find 2/3, 0, and minus 1/3. So in this case, the isospin wave function for the 3 Pion system is going to be square root of 2/3 to 0 minus square root of 1/3, 0, 0. The state 1, 0 is forbidden. Now we consider the last case. So for I pi pi equal to 2, okay? And in this case, the Klebsque coordinate table is the following. 1 times 1, and we have 3, 2, 1, 0, 0, 0, 0, 0, and the values are 3/5, 0, and minus 2/5. So in this case, the total wave function will be square root of 3/5, 3, 0, minus square root of 2/5, 1, 0. So overall, if we now consider all cases or possible cases, then the following 4 isospin states are possible for the pi plus, pi minus, pi 0 system. So the 3, 0 is possible, the 2, 0 is possible, the 1, 0 is possible, and the 0, 0 is possible, each with its proper probability, so squared amplitude, given in terms of the Klebsque coordinate coefficients. Okay. Now, let's consider the second case, so the system of 3 neutral pions. So I will take a new page. Okay, so now the system we are interested in is the pi 0, pi 0, pi 0. And we essentially proceed in much like the same way. So we first consider the first 2 pi 0. So the I3 for the pi 0 is I3 pi 0 plus I3 pi 0, that is 0 plus 0 equals 0. Then we compute the total, I pi 0 minus I pi 0, I pi 0 plus I pi 0. And so here, the only possible values are, this ranges from 0 to 2. So the possibilities are 0, 1, or 2. So let's take now the Klebsque coordinate coefficient. The table we need is the following. 2, 1, 0, 0, 0, 0, 0, 0, 2/3, 0, minus 1/3. And so for the first two, we have again 2/3, 2, 0, minus square root of 1/3, 0, 0. Now, let's add now the third pi zero. Okay. So the total isospin, first component, is the sum of the third component for the two Pion system plus this additional pi zero. So this is again 0 plus 0 equals 0. Then we compute the total. And here we have now two possibilities. So the total isospin for the three neutral Pion system can be 1 for I pi 0 equals 0, or can be 1, 2, or 3 for I pi 0 equal 2. So let's consider again the two cases separately. So for I pi 0 equals 0, we have only one possibility. So the isospin wave function will look like, for the three pi zeros, this will look like just 1, 0. For I pi 0 equal 2, instead, we have to combine the two isospin states through the Klebsque coordinate coefficients. So this is the same situation that we have seen before. So this is I3 pi 0. We found again square root of 3/5 30 minus square root of 2/5 10. Okay. So for the system of the three neutral pions, the only possible states are 30 or 10. So we have only two possibilities in this case. In the previous case, we had 4 different possible states. Okay. So if there are no questions, let's move on to the next problem. Okay, problem 5.2. Find the relation between the cross sections of the following processes. So we have pi minus proton into sigma 0 k0, pi minus proton into sigma minus k plus, and pi plus proton into sigma plus k plus. Okay, where the sigmas are among the are 3 hyperons, as we have seen. Okay, so they are among the 3 lightest strange hadrons. So let's switch back to Blackboard. All right. So this is problem 5.2. So let me write down also here the 3 cases. So case A, the reaction A is pi minus proton into sigma 0 k0. Case B is pi minus proton into sigma minus k plus. And case C is pi plus proton into sigma plus k plus. And before solving the problem, let me summarize what we know about the isospin assignment of each of these particles. Okay, so as you know, for the proton, we have 1/2, 1/2. For the neutron, we have 1/2 minus 1/2. For the pi plus, we have 1 plus 1. For the pi minus, we have 1 minus 1, followed by 0, which we don't need, but okay, let me just write for completeness. We have 1 and 0. Now we have the two kaons. So the k plus is 1/2, 1/2, and the k0 is 1/2 minus 1/2. So this is the first isospin doublet for the kaons. Then we have the k0 bar. This is 1/2, 1/2, and the k minus is 1/2 minus 1/2, and this is the other isospin doublet. And then finally we have the three sigma particles. Let me just remind you the quark content of the kaons. So the k plus is a u s bar object. The k0 is a d s bar object. The k0 bar is an s u bar object, and the k minus is an s d bar object. Now, let me give you the isospin states for the three sigmas. So the sigma plus is 1 plus 1, and it is a UUS baryon. Then we have the sigma 0, that is a 1, 0 isospin state, and it is a UDS baryon. And finally, the sigma minus is a 1 minus 1, and the quark content is DDS. Okay. So as you see, the sigma plus, sigma 0, sigma minus form an isospin triplet, okay, quite similar to the one of the three pions, okay, with the same quantum numbers, isospin quantum numbers. Okay, having said all that, let's start solving the problem. So let's consider, first of all, the first reaction, pi minus proton into sigma 0, k0. And so we proceed in the usual way. So for the initial state, the third component will be the sum of the third component of the pi minus plus that of the proton, that is minus 1 plus 1/2 equal to minus 1/2. Now the total isospin, I pi minus minus I proton, I pi minus plus I proton. So we have 1 minus 1/2, 1 plus 1/2. And so the possible assignment are 1/2 and 3/2. And both values are possible because the third component is just minus 1/2. Okay, so we have to combine them in the usual way. So let's take the Klebsque order coefficients. This is the table 1 times 1/2. Then we have 3/2, 1/2, minus 1/2, minus 1/2, minus 1 plus 1/2. And the values are 1/3 and minus 2/3. So for the initial state, we have square root of 1/3, 3/2 minus 1/2, minus square root of 2/3, 1/2 minus 1/2. So now we have to compute the final state, wave function. So I'll take a new page. Now, for the final state, we have I3F is equal to I3K0 plus I3 sigma 0. That is minus 1/2 plus 0 equal to minus 1/2. Then we compute the total isospin. ik0 minus I sigma 0 ik0 plus I sigma 0. This is 1/2 minus 1, 1/2 plus 1. And so overall we have two values, 1/2 and 3/2 again. And again, both are possible. So in this case, the Klebsche-Gordon table is the following: 1 times 1/2, 3/2, 1/2, minus 1/2, minus 1/2, 0, minus 1/2, and the values are 2/3 and 1/3. So the final state isospin wave function will be square root of 2/3, 3/2 minus 1/2, plus square root of 1/3, 1/2 minus 1/2. Okay, now we can compute our cross-section. So the cross-section for the process pi minus proton into sigma 0 A0 will be proportional to the following squared amplitude. So final state, our isospin-dependent Hamiltonian initial state all squared. And so let's substitute here all we have obtained. So this is square root of 2/3, 3/2 minus 1/2, plus square root of 1/3, 1/2 minus 1/2 for the final state. Then we have our Hamiltonian term, and then we have the initial state, square root of 1/3, 3/2 minus 1/2, minus square root of 2/3, 1/2 minus 1/2 squared. So let's take all the products. Square root of 2/9 of 3/2 minus 1/2 hi 3/2 minus 1/2 minus 2/3 3/2 minus 1/2 hi 1/2 minus 1/2 plus 1/9 1/2 minus 1/2 hi 3/2 minus 1/2 minus square root of 2/9 1/2 minus 1/2 hi 1/2 minus 1/2 full stop. So we have two contributions, but only two of them conserve isospin. The other two are isospin violating, so these will not contribute to the cross-section. And so we can express our cross-section as square root of 2/9 m 3/2 minus square root of 2/9 m 1/2 squared. So if you like, we can write sigma pi minus proton that goes into sigma 0 k0 must be proportional to 2/9, and then we have m 3/2 minus m 1/2 squared. This was the first one. So let's now go quickly to the other two, and then we construct the ratios. So the second reaction we want to study is pi minus proton that goes into sigma minus K plus. So the initial state is the same as before, so we can immediately write that I is equal to square root of 1/3, 3/2 minus 1/2 minus square root of 2/3, 1/2 minus 1/2. Let's now move on to the final state. So the third component of isospin is I3 K plus I3 sigma minus, that is plus 1/2 minus 1, it is minus 1/2. Then if you compute the final state total isospin, you get two values, 1/2 and 3/2 again. So we have to take the proper Klebsche-Gordon. So we have 3/2, 1/2, minus 1/2, minus 1/2, minus 1, plus 1/2, and from the table you obtain 1/3 and minus 2/3. And so we can write down easily the final state isospin wave function as square root of 1/3, 3/2 minus 1/2, minus square root of 2/3, 1/2 minus 1/2. And so we can now compute our cross-section for the pi minus proton into sigma minus K plus, which is proportional to, as usual, F hi I squared. So we substitute. Three half minus 1/2 minus square root of 2/3, 1/2 minus 1/2. This is the final state. Then we have hi, and then we have the initial state, square root of 1/3, 3/2 minus 1/2, minus square root of 2/3, 1/2 minus 1/2, all squared. Okay. As before, we can take the product, and we will find out that 2 of the 4 contributions are isospin violating, so they cannot contribute, they must be 0. And so overall, just after a couple of passages, you will find out that this is 1/3 and 3/2 plus 2/3 and 1/2 squared. And so we can write down the cross-section for this second process, sigma minus K plus, proportional to 1/9 and 3/2 plus twice and 1/2 squared. Okay, let's now attack the last reaction. Okay, I can see it is now a pi plus proton that goes into a sigma plus K plus. So the third component of isospin in the initial state is that of the pi plus that of the proton, that is plus 1 plus 1/2 equal to 3/2. The total isospin in the initial state so at the end you obtain two values, i.e. equal to 1/2 and 3/2, but since your third component is already 3/2, then the only possibility is that the total isospin is 3/2, so cannot be 1/2. And so the initial state wave function is simply 3/2, 3/2. Let's now work out the final state, isospin. So the third component is 1/2 plus 1, that is 3/2, as we expected. And you will find out that the final state total isospin is just 3/2. So for the final state wave function, we have 3/2 and 3/2. So in this case, we can easily write down the cross-section to be proportional to f hi I squared, which is now simply 3/2 3/2 hi 3/2 3/2, and so this is simply m 3/2 squared. So let me write down the same way as the other. So with pi plus p into sigma plus k plus will be proportional to m 3/2 squared. So now we have all three of them, so we can now put them all together. So sigma A stays to sigma 2, stays to sigma C as 2/9 of m 3/2 minus m 1/2 squared stays to 1/9 of m 3/2 plus 2 m 1/2 squared, which stays to m 3/2 squared. Okay, so this is the ratio of the three cross-section just based on conservation of isospin in the strong process. One can study here two limit cases. Okay, so suppose for instance that you are in a regime where m 3/2 is much greater than m 1/2. So one can neglect m 1/2 compared to m 3/2. And so in this case, the ratio of the cross-section will be simply 2/9 to 1/9 to 1, or which is equivalent to 1 to 9. Or the opposite case where m 3/2 is much smaller than m 1/2, so you can neglect m 3/2. Then in this case, sigma A to sigma B to sigma C will be 2/9 to 4/9 to 0, or equivalently to 4 to 0, or even 1 to 2 to 0. So the second will be double than the first one, and the third one will be 0 in this case. Okay. If there are no questions, we can move on to the last problem. Okay, so this is now about decay. So the neutral baryon of sigma 0, 1915 has isospin 10. Calculate the following ratio of decay rates. Okay, so of course what we have learned about reactions if the applies also to decays, as long as the decays are regulated by the strong interaction. Okay, so that one can impose isospin conservation. So let's move on to the whiteboard. Okay, so this is problem 5.3. Let me write down the three. No, sorry, wait, just in one case here. Okay. So let me copy here the date of the text. So we know that the I3 of the sigma 0 is 10. And we want to calculate the ratio of decay rates of the sigma 0 decaying into a K0 bar neutron divided by the decay width of the sigma 0 decaying into a K- proton. So this is our goal. Okay, so let's proceed in the usual way. So let's first find the isospin of the composite system, K0n and K minus proton. So let's start from the K minus, what is that? The K0 neutron, yes. So I3 for the K0 bar neutron system. This is I3 of the K0 plus I3 of the neutron. That is 1/2 minus 1/2 equal to 0. And the total isospin, K0 bar minus neutron, K0 bar plus neutron. So this is 1/2 minus 1/2. One half plus 1/2. And so overall, we have two possibilities. So either 0 or 1. And they are both possible since the third component is just 0. So we have to combine them with the Klebsche-Gordon. The table we need is now 1/2 times 1/2, 1, 0, 0, 0, 1/2 minus 1/2, and the values are 1/2 and 1/2. So the isospin wave function for this final state K0 bar neutron is square root of 1/2, 1, 0 plus 0, 0. Let's now consider the other final state. So the K minus proton. So I3 of K minus proton is going to be I3 K minus plus I3 proton. That is minus 1/2 plus 1/2, again 0. Total isospin. So this is 1/2 minus 1/2. One half plus 1/2. And so we have again two values. That is K minus P equal to 0 and 1. And again, they are both possible because the third component is 0. So we need to combine them with the proper Klebsche-Gordon. 1, 0, 0, 0. In this case, we have minus 1/2 and plus 1/2. And the values are 1/2 and minus 1/2. And so in this case, for this final state, the isospin wave function is going to be 1/2, 1, 0, minus 0, 0. There's a question?
Yeah, sorry, can you remind me the order in which you were putting the in the table? How is it defined?
So the quantities that appear in the table here?
Yes.
Okay, I think it's better. Okay, yes.
Because
something not corresponding.
No,
so this.
Yeah, the question was which one were in a Klebsche-Gordon on the left side where you've got the I3 of the two. It's obviously not commutative, right? So.
That's a good question. I think that should be actually, so the order should not matter. And you, let me see. So let's see together. Actually, so let's move to the Klebsche-Gordon. square. I think the order should not matter as long as you have the. Oh no, it does actually. It does. The order does matter, yes. Good question. I have to think a little bit. I don't have a ready answer for this.
Thanks.
Okay. I will think about it and let you know. Thanks for asking the problem. So let's just complete the problem for the moment. Okay, let me take a new page here. So if you remember, we are dealing with a decay of the sigma zero, and we know from the text that the isospin wave function 1, 3 for the sigma zero is 1, 0. This we know from the text. Okay, so this is our initial state, and then we have the decay. So let's consider the two decays separately. So the sigma zero goes into K0 bar neutron. In this case, the decay width for the K0 bar neutron must be proportional to, as we've calculated, 1 of square root of 2, 0, 0, plus 1, 0, hi, and then we simply have 1, 0 for the initial state, our sigma squared. So here we have 1/2 we can put outside. Then we have 0, 0, hi, 1, 0, plus 1, 0, hi, 1, 0. Only the second of this contribution can survive, because only the one on the second ensures isospin conservation. So this is just 1, 0, hi, 1, 0 squared. It is m1 squared divided by 2. Now we do the same exercise for the other decay mode. So the sigma zero now decaying into a K minus proton. So the decay width is proportional to 1 of square root of 2. Then we have minus 0, 0, hi, 1, 0, plus 1, 0, hi, 1, 0, squared. And this is m1 squared divided by 2. And so now when you take the ratio of the two decay widths, this is just m1 squared divided by 2 divided by the same quantity. So the ratio is exactly 1. And this means that indeed these two decay must have the same decay rate or the same probability. Okay, this was the last thing about today. I will think about your question, Ben, and then I will tell you next time. Hopefully I found some answer. And if there are no other questions, we will see again on April 8th after the Easter break. Okay?
Tomorrow is off in
yeah,
Italy.
Tomorrow is vacation, yes. We don't have lesson tomorrow.
Okay.
Okay, so happy Easter. Enjoy your vacation. I don't know if we can really call them vacation in this situation, but okay, at least try to relax a bit. And see you on April 8th.
Thank you. Happy Easter.
Thank you.
Arrivederci, prof.
Arrivederci.
Arrivederci.
Arrivederci.